What's up, fellas? Sorry I can't make it to class. I bet you guys are all having a blast, though. Today I'm going to talk to you guys about a standard finite element model of a pressure-sensitive adhesives stress distribution that I made for this FEA class. To give you guys some background on my project, transitional flow characteristics of aircrafts are being investigated through measuring devices attached to their surface. The figure shows an illustration of a simplified device attached to the surface of an aircraft. In order to have a strong bond to the surface, an industrial-grade pressure-sensitive adhesive is being used. According to the adhesive manufacturer, the adhesive will fully cure when 15 psi is applied for a minimum of 20 minutes throughout the material. Concern for the adhesive's bond has been growing, and fear of its poor bond providing misleading data or yielding has become an issue. Due to the electronics in the instrument, the device cannot be loaded through its middle section. Currently, the cure load is achieved through a constant compressive force of 112.5 pounds applied through a plate placed directly on top of the device. The applied force is obtained by multiplying the manufacturer's minimum cure pressure by the adhesive's applied area. A finite element model can show whether the current loading makes the adhesive stress distribution meet the minimum cure load required. If the loading is inadequate, different loadings or design parameters can be suggested for better results. The model was simplified through defeaturing, symmetry, and loading simplification. As you can see in the image, a symmetrical model was used with only 1 foot, and this is because the stress distribution seen in 1 foot should be identical to the second foot. Then the device was modeled with shell elements and the adhesive with solid elements. There were 4 different tests conducted on the finite element model. The first one was a baseline, and it was the original loading, which again uses point loads as shown in the figure. The second test was additional loading. So this was done by leaving the 2 point loads on the wall, but also applying point loads on the feet, a set amount of inches away from the edge, as shown in the figure. The third analysis was adding a fillet to the wall. This was done by partitioning the bottom surface of the instrument and redefining its respective section definition, and this can be observed in the figure. And the last one was simply incrementing the foot's thickness, done by modifying the section definition of the feet. All the tests conducted on the finite element model produced very interesting results, giving us a better understanding of ideal cure load conditions. It is important to note that all stress distributions on the graph follow the expected trend, with really high stress directly under the corresponding point load and tapering off steadily. Another surprising result was that when incorporating a higher thickness on the walls to produce the effect of a fillet, there were no substantial effects on the stress distributions, as can be observed in the graph. A thickness of 0.25 and 0.35 inches slightly dispersed the stress, but did so insignificantly enough that it did not increase the minimum cure load met areas. The additional load analysis showed very promising results. It did increment the minimum cure load met areas. However, it almost tripled the maximum stress observed from the baseline loading to a value of 240 psi. This is due to the point load on the feet being so close to the adhesive. The additional parameter investigated was increasing the thickness of the feet from 0.125 inches to 0.25 inches. The results showed that the maximum stress was decreased to 60 psi from a baseline of 85.2, and also the minimum cure load met areas were slightly increased as shown in the figure. Lastly, it was also observed that the baseline original loading test, which is shown in the graph with a dotted line, had a very small portion of the adhesive actually feeling the minimum cure load required, which is not so good. Again, the results for the original loading showed us that it does not provide a very good stress load on the adhesive. Out of all the tests, the two parameters that really made a difference were increasing the thickness of the feet and using a different loading plate, which can provide additional loadings on the feet. These results suggest a better design would be one as shown in the bottom picture in this slide. This improved design increments the minimum cure load met area by roughly 166% compared to the original baseline loading. That the other image in the slide shows adhesive stress distribution for baseline in the top and the improved design on the bottom. The contour is limited to show a 15 psi minimum cure load met area in black, so black is good. Also, due to the thick foot, the maximum stress observed isn't as high as the result observed initially. The maximum stress in the adhesive is 117.7 psi, only a 37.6 increase from the original loading. However, before implementation of this improved design, the aircraft skin where it's being attached to should be taken into consideration. This new maximum stress may be over the yield stress of the skin material. These results are significant because they can be broadly applied. They accurately show the stress distribution on the adhesive loaded through similar instruments. Later tests can be tailored specifically to surfaces it will be attached to, so material yield tests can be conducted. Additionally, further analysis should be conducted on fillets with solid elements to verify the poor results obtained in this report. Well, that's it, folks. Thanks a lot for your time. Thank you for listening. And I want to give a quick shout out to Professor Schuster for helping me out. Thanks a lot, man. If you guys have any questions, feel free to email me. My email address is on the slide, and I'll reply promptly. Have a good break, guys.